So good afternoon, everybody. My name is Andrea Possemato, and I'm a PhD student at Eurecom. Today, I'm going to present you the work ClickShield, are you adding something towards eradicating clickjacking on Android. This work has been done in collaboration with other researchers from Georgia Tech University and University of Milan, and I would like to thank all my co-authors. So let's start first by explaining how clickjacking works. In a clickjacking attack, the goal of the attacker is to lure the user into clicking some specific portion of the screen. Normally, this click allows the attacker to gain additional permission and privileges or perform some sensitive operation on behalf of the user. So, let's say the attacker wants to target the OK button. How we can lure the user into clicking it is just by covering the original activity with a fake window, create a fake button just on top of the original one, so that when the user clicks, the clicks gets propagated to the target button. To mount this kind of attack, the attacker needs only one permission, and the permission is named the system alert window. This permission is automatically granted by default to every application that is downloaded and installed directly from the official Google Play Store. As we can see from the documentation here, a malicious application asking this permission is allowed to create windows on top of all the other applications. This mechanism was available since API level 1, and what is important to understand here is that the developer, or in this case the attacker, can control the position, the shape, the color, even the transparency of all the overlays he is drawing, and also if the click must be processed in the context of the window or it must be propagated to the application below. It's also very common to find benign applications using this kind of permission to draw some overlays, and probably the best example is the Facebook Messenger application. So Google knew about this problem, so they introduced a new defense mechanism named obscure flag. How it works is pretty simple. So now with this flag, the developer can protect sensitive buttons, so that when the user clicks, he can check if the button that was clicked was covered by any kind of overlay. So let's say this example, and this time the developer protected the OK button with this flag. So the user draws his malicious overlay on top of the application, the user clicks the OK button, but since it was protected with this obscure flag mechanism, the click is rejected, and the application is informing us that because the button was obscured, they cannot verify our response. Unfortunately, this obscure flag mechanism comes with a big problem. We can protect buttons only. This means that all of the other components of the UI are left unprotected. And what if the attacker is going to cover all of the part of the screen except the OK button, and then he creates some fake content to lure the user into clicking the OK button? Since the OK button is not covered by any kind of overlay, at the time of the click, the application cannot reject it. This attack is named context hiding attack. It was presented by some of my co-authors at SMP 2017. This is basically a cat and mouse game. So Google knew about this context hiding attack, so they decided to introduce a new defense mechanism named idle overlays. How it works is pretty neat. Now the developer can protect one activity or one entire application with this mechanism, so that when the application is started, all the overlays are automatically removed by the system. So to recap, we started with the traditional clickjacking attack, and it was defeated by the obscure flag. Unfortunately, obscure flag was not good enough, so we had the context hiding attack bypass. But now it seems like that Google, with the idle overlays, is going to eradicate both clickjacking and context hiding. Unfortunately, this is not the case. This protection mechanism here is too powerful. We think it's too powerful, so third-party application cannot ask cannot use this defense mechanism. And it's only available to system application. This means that, okay, we have defeated clickjacking, but context hiding is still a problem. So now we wanted to understand if at least application were using this kind of defense mechanism. So unfortunately, we discovered that this is not the case. So we did a study of this countermeasure adoption, and we figured out that it was not used due to a lot of problems. Okay. The first one is a usability problem. We found that there is a big category of application named screen filter, which has as the main goal the one of drawing this kind of overlay on top of the application. This means that if we were using some application that is protected with the obscure flag, and at the same time we are using some screen filter, we're having some usability issue. This means that we need to disable the screen filter application, then interact with the application, and then enable the screen filter again. To check if at least also top application were using this kind of defense mechanism, we started to look at top apps. But we were able to attack Google Play Store, Gmail. We were able to send arbitrary email on behalf of the user. It was the same for Google Authenticator. We were able to steal OTP tokens. It was the same for Twitter, Facebook, even Google Drive, even Signal and WhatsApp. Basically, all of the applications that we analyzed, we found out that they were not using this kind of protection mechanism. So clickjacking is still a widespread problem. We did the disclosure process with the vendors, and the reaction confirmed that this main problem is a usability issue. So Twitter said that since obscure flag mechanism is going to introduce some usability issue, they are not going to use it. Signal said that since this defense mechanism is not effective enough, they are not going to adopt it. And the reply that we have was the same for Facebook, WhatsApp, Instagram. We were able to find vulnerabilities on all of these applications, and they said that there is a balance between security and usability, and this defense mechanism is going to break this balance. So we have a big problem. The only available defense mechanism to defeat clickjacking attack is suffering to backward compatibility problem. So the next things we did was try to understand how overlays are used by good application and try to understand if it's possible to differentiate them amongst the malicious one. So to do so, we did a systematic survey when we analyzed around the 300 applications declaring using the system alert window permission, and we downloaded those applications from both the official Google Play Store and F-Droid. And also we downloaded a lot of these screen filter applications, which we saw are the root cause of this usability problem. So we were able to identify two main categories. The first one are widgets. This kind of application they have one goal, to inform the user that something is going on. And as we can see here, they are sharing three main features. The first one, they are both clickable. This means that when we are clicking the overlay, a new application is started. They are both opaque. They are showing some content to the user. And all of them are drawing at the margin. The second big category of application that we identified is a screen filter. And if you think that these applications are not used by a lot of people, this table shows that these applications are used by millions of users. All of these applications are sharing three common features. The first one, they are all drawing overlays that are pass-through. This means that the click is propagated to the application below. They are both semi-transparent, and all of them are drawing full-screen overlay. So this survey allowed us to draw some key observations. The first one is that the central portion of the screen is not covered when we are using widget, because we saw that all of them were drawing something at the margin. Or all the pixels are modified in a uniform way, and the context is clear if we are using screen filter. As we saw, all the screen filter are drawing some full screen and semi-transparent overlay. This means that if a user is using this kind of screen filter, he can understand what's going on. So clickjacking is not a problem. It's very difficult to understand and distinguish between benign and malicious overlay just by looking at this kind of feature. So we saw that some previous attempts tried to understand if overlay was benign or malicious just by checking if it was clickable or configured as pass-through. So they said that if the click is not propagated, we cannot mount clickjacking attack. Unfortunately, with this context hiding attack, we were able to mount clickjacking just by using clickable overlay. So this is a bad feature to use. The second one is just by checking if the overlay is opaque or semi-transparent. The idea is that if you have some opaque overlay, you are trying to modify the context of the screen, so they're bad. And semi-transparent overlay drawn by screen filters are good because they are not trying to deceive the user. Unfortunately, what we saw is that we were able to gain some opaque result, as we can see at the bottom of the screen, just by overlapping a lot of semi-transparent overlays. So just checking if an overlay is semi-transparent or opaque is not enough. So also this feature is not good. Based on this observation, we designed our system that we named it ClickShield, and our system is based on some key ideas. The first one is that we need to focus our attention on the central part of the screen. Our survey and our analysis show that all of the applications that we analyzed were showing some sensitive or security context in this part of the screen. So this part of the screen is very important if we want to understand if something bad is going on. The second one is that since the screen filter overlay were the root cause of all the backward compatibility concern for obscure flag, we need to allow these semi-transparent uniform overlays. So screen filter are good. The third one, we did our ClickShield implementation as a framework modification, and we truly believe that this is important. Those kind of feature, if the overlay is drawn on the central part of the screen or if it's semi-transparent, are information that are only available if you are going to modify the Android framework. Every kind of defense mechanism that tries to work at the user level space is not gonna work. So let's first check how the alpha blending works. Alpha blending is the algorithm used by the system when some overlays are drawn on top of the screen. So let's say we have the target application the attacker want to attack. What he can do is try to cover some portion of the screen just by drawing one overlay or multiple overlays. All of the overlays at the time of the rendering are meshed on top of this target app, and as final result, we have the final render. Our system takes as input the cropped version of the target app, since we saw that widgets that are drawn at the margin, they're not problematic, and also the final render. Basically, what we have as input is that the final render shows us what the user sees when he's interacting with the application, and the target app input shows us what the app thinks the user is seeing. Then we ask a question, and we are check if those two elements are differ. If they are differing, we need to focus our attention and try to understand what is the net effect of all of these overlay. Unfortunately, this is not very easy. This is the formula used during the alpha blending process. As we can see, the final render is a weighted average of the overlays and the target app. And also we have an alpha value. This alpha value is very important because it's going to tell us if the overlay drawn on top of the application are semi-transparent or opaque. Unfortunately, our system takes as input the final render and the target app representation, but we don't know the overlays and the alpha value. We don't know this value because how the alpha blending works, the final render and the target app are the only two available input that we have from the system. So we are in a situation where we have four incognitas. The four incognitas are made by the RGB triplet and the alpha value, but we have only three equations, so we have a problem here. We had an intuition. If we are going to consider a pair of pixels, and we are going to assume for a moment that the overlay are uniform, then we can share the alpha between those pixels. By doing this, we are in a situation where we have four incognitas, RGB triplet and the alpha value, but this time we have a 6 equation. So now it's better. So we are going to write our system of equation. Here we wrote only 2 of them, but keep in mind that color means RGB. So we will have 3 different formulas for every kind of equation here. From this system of equation here, we can extract a candidate of alpha. And this value of alpha, unfortunately, due to the rounding process done by the system, is not very perfect. To reduce the error, we repeat this process multiple times until the error on alpha is small enough. This value of alpha is very important because here we didn't extract all the overlay surface, so we just computed one single value, and this single value tells us if the overlay drawn on top of the target application are full screen. And here, to confirm this assumption, we are going to check pixel by pixel if the final render and the target application are differing. We are going to do this because the attacker here has some pixel level control. So maybe the attacker is changing only some portion of the screen. And if we check here, and if you see here a mismatch between the final render and the target app, we are going to raise a warning. Then the alpha value can tell us that the overlay drawn on top of the target application are opaque, and this means that the context is somehow changed. And so we are flagging this sample as potential problematic because for us something bad is going on. This means that the central part of the screen that for us is critical is changing in some bad way. The third part, which is the most problematic one, is when we have some semi-transparent overlay, because we need to understand now the net effect of all of these overlay. To do so, we are going to compute a new metric that we call the uniformity score. So now that we have the value of alpha, we can easily compute all the overlays. And on these overlays, we are going to verify the uniformity assumption that we did before. To do so, we need to compute the uniformity score, and we're going to compute this with this formula. And basically, the value of gamma tells us that the lower this value is, the more uniform the overlay is. So if we are seeing that the gamma value is low, it's good. If it's very high, probably it's bad. So we wanted to test our solution against some benchmark, but we didn't find any one of these. So for this reason, we also create a benchmark to evaluate our clickjacking approach, and we are going to release it. We named the dataset ClickBench, and at the moment, it's composed by 104 test cases. 47 of them are benign, and 57 of them are problematic. This problematic bucket, we are going to have all of the known sample of malware that are available, and like clickjacking and context tagging attack. And also we added some synthetic test case to explicitly stress test our own system. So by looking at the evaluation, we were able to spot 46 out of 47 benign samples, and we had only one false positive. The false positive is this one, is a video player preview from F-Droid. As we can see here, this is a bad example because the application is going to cover the central part of the screen in an opaque way. And this is going to collude with the key idea number 1 and the key idea number 2. This is, let's say, not a big deal because we just ask the user to confirm the click without showing him the overlay. For what concerns the problematic test case, we were able to spot all of them. For what concerns the performance, we ran all the example hundreds of times on a real phone, and the minimum execution time is around 12 milliseconds. We think this is negligible overhead for the user. So here, let's say if our metric is good, as you can see at the bottom, basically all the benign samples are very close one to each other. And as we can see, the malicious one are very distant from this one. Here, we also were able to spot a real example where context ID attack was used to gain additional privileges. Here we can see that the attacker changed the context of the text shown to the user, and also this sample was published after our ClickShield solution was made. So we were also able, without doing any kind of modification, to spot this kind of sample here. And also, if you can see here, here is a synthetic example that we explicitly wrote to stress test our own system. And here it's very difficult to see, but the original price was $2.99. And here the attacker draws a fake overlay to change the price just by changing the first dollar. So now the user thinks that he's going to pay the application €1.99 euro. As we can see here, our uniformity score was able to detect only this little subtle pixel modification. And as you can see, the distance between the latest benign app and the first malicious one is very large. So we decided to put an empirical threshold of 100 for the uniformity score. So to conclude, we showed how clickjacking on mobile is still an open problem. A lot of these top applications are still vulnerable today. We proposed ClickShield, and we're going to publish also and release it after the conference. And ClickShield is a new defense mechanism to eradicate clickjacking attack without introducing some user experience issue. And we really hope that Google is going to be inspired by this work, and they're going to do something to eradicate this problem, maybe by adding some native defense mechanisms to defeat this kind of attack. That's all. Thanks.
Sure. Rob Cunningham, thank you very much for the work. I like it. I have a question, though, about alpha. Is it the case that that value has to be the same across the entire overlay, or can that change depending on where you are on the image?
Thanks for the question. Basically, you are saying that if the screen filter are modifying in a different way the screen, all the tests that we have show that all of these kind of applications are modifying the screen in a uniform way. You cannot specify that you want the top part of the screen darker than the lower one. So this was a strong assumption for us. So yeah.
And that's what they do, but is it that they must do it that way, or is it possible to do it? Because that's an obvious attack against this system.
Yeah, they can do it, but with our ClickShield system, we can spot this kind of situation. I mean, if the application is completely covering one portion of the screen and let the rest of the screen semi-transparent, for us this is a bad indicator. And so we are going to flag this sample as at least suspicious. And then we are going to ask the user to confirm the click.
Thank you.
You're welcome.
Hi, I'm Fabio Pierazzi from King's College London. I have a question about the threat model. Like in the previous example, you showed example of the Pokemon.
Yep.
And using the overlays to like click the OK button.
Yeah.
But does it? I mean, how does the attacker know? Like, what is actually generating the overlays? Like, is it? I mean, for example, if I'm using, if I'm showing this Pokemon thing over a permission window, is it because the victim installed the attacker application, or is the attacker able to interact with the current overlay?
Okay, thanks for the question. The threat model here is a local attacker that runs only with this system alert window permission. So this is the only permission the attacker needs. And basically, with some intent, he can start some very specific activity. For example, let's say that this target activity was exported. So the attacker can start the intent by using an activity. And then from the background, he can draw some overlays on top of it.
Okay, so but the user needs to install an infected app anyway.
Yeah. The threat model is a local attacker, but he doesn't need to gain root privileges, for example.
Okay.
It's just, let's say that you publish a malicious application on Google Play Store, and then, or maybe just a malicious library on a third-party app, maybe. But yeah, here the application is running as a trusted application, so no more privileges are asked, only this system alert window permission.
Thanks.
You're welcome.
So you mentioned you would like Google to get inspired by this. So do you, with inspiration, you mean they will adopt exactly this approach where you measure the alpha, or do you see any other ways to integrate a defense? Because, for instance, from your ideas, from this great talk, from the ideas, for instance, I think, for instance, the system alert permission seems to be a little bit ambiguous, that you can draw various kinds of overlays to maybe break this down potentially, and in the system permissions or something.
Basically, you are asking if we think that Google needs to implement this solution or another one?
How could they go for it? For instance, do you think it would make sense to break the system alert a little bit down based on your ideas, for instance?
For sure, this permission is a very big permission. It's a very dangerous one. So maybe, let's say, by reducing the things that a malicious application can do is a good approach. But we also think that since this problem is, we saw that is widespread, maybe some native implementation to defeat this kind of attack is the good things to do. Because basically the obscure flag is neither used by application and it's also bypassable. So it's basically not effective.
Further questions? Thanks.